Hello students. This question is presented by teacher Isa Al-Nabani. Today we will evaluate one of the most famous integrals in mathematics, the Gaussian integral. We want to evaluate the integral from negative infinity to positive infinity, of e to the power negative x squared, dx. This function has no elementary antiderivative, so we need a clever trick. The trick is to square the integral. We write I squared as the product of two copies of the same integral, using a different variable, y, for the second one, since the two integrals are independent. By Fubini's theorem, the product of two separate integrals can be written as one double integral. Since e to the a, times e to the b, equals e to the a plus b, we combine the exponents to get e to the negative, x squared plus y squared. This double integral covers the entire xy plane. Since the integrand depends only on x squared plus y squared, we switch to polar coordinates, where x equals our cosine theta, and y equals our sine theta. Substituting, and using the identity cosine squared theta plus sine squared theta equals 1, we find that x squared plus y squared simply equals r squared. Next, we transform the area element. In Cartesian coordinates, a small area is dx dy. In polar coordinates, a small region has arc length r d theta, and radial thickness dr, so its area is r, dr, d theta. Notice the extra factor of r. Since our region is the entire plane, r ranges from 0 to infinity, and theta ranges from 0 to 2 pi. Our integral becomes a double integral of e to the negative r squared, times r, dr, d theta. We evaluate the inner integral using substitution, let u equal r squared, so du equals 2r dr. This turns our integral into 1/2, times the integral of e to the negative u, du, from 0 to infinity, which equals 1/2. Now the outer integral is simply 1/2, integrated with respect to theta, from 0 to 2 pi. This gives us 1/2 times 2 pi, which is pi. So I squared equals pi, and since I is positive, I equals the square root of pi. This is our famous final result. Here is a beautiful insight: this same integral, without the exponential term, gives exactly the area of a circle. If you integrate r over r and theta, across a full circle of radius r, you get pi r squared. That's because a thin ring at radius r has circumference 2 pi r, and stacking all these rings from the center outward builds up the circle's area. The 2 pi in our final answer is the very same 2 pi from going once around the circle. This elegant proof combines calculus, symmetry, and polar coordinates beautifully. Keep practicing, and I will see you in the next question.